So our next speaker will be Isaac Bodemann, and he was from the University of Texas at Austin, and also going to give us a great presentation.
Hello everyone, I'm Isaac Bodemann, and this summer I researched the growth and characterization of monolayer molybdenum diselenide using chemical vapor deposition. So, Moore's law states that the processing power of integrated chips will double every 2 years. But as silicon is beginning to reach its physical limits, Moore's prediction may very soon come to an end. However, there is still hope. Molybdenum diselenide belongs to a group of materials called transition metal dichalcogenides, or simply TMDs. This new group of materials has the potential to uphold Moore's law, and they have become heavily researched over the last few years. TMDs consist of one transition metal atom sandwiched between two chalcogen atoms. And what makes TMDs unique is that they transition from an indirect band gap in the bulk material to a direct band gap when in monolayers. And this property makes them exceptional for optoelectronic and flexible device applications. So the primary motivation of my research is that TMDs are most often acquired using mechanical exfoliation, which is basically just tearing away layer by layer of the bulk material using tape until you acquire a monolayer. And this process is just far too inefficient and time-consuming for commercialization. But chemical vapor deposition, on the other hand, is able to produce large quantities of TMDs at a much faster rate. So the method that I'm researching holds great promise for future industrial production. And the goals of my research is to, first I sought to optimize the growth of large MOSE2 monolayers using chemical vapor deposition, but also to analyze the effect of changing various parameters on the growth process. So to create my samples, I started by loading selenium powder and molybdenum oxide powder into two separate ceramic boats, as you can see right here. I then placed a silicon oxide wafer on the molybdenum oxide boat and loaded it into the center of the furnace. Next, I loaded the selenium boat into the same tube, but just outside of the furnace, as it has its own heater. Then I heated up the furnace, vaporized these precursors, and they would react to form molybdenum diselenide on my silicon-based wafer. Then finally, I cooled the furnace and removed the sample for characterization. So for the first step of characterization, I used an optical microscope, basically just to see if anything had actually grown on my sample. I also used it to find potential monolayers that I could analyze further. And this image is an example of a optical microscopy image, and it just illustrates what MOSE2 monolayer domains look like. You can see those here. Next, I performed Raman spectroscopy on the potential monolayers. So if the Raman peaks were consistent with published reports in the literature, then I was able to determine whether the material I grew was actually molybdenum diselenide or something else. The final step of characterization was photoluminescence spectroscopy. And by comparing this peak to the literature, I was able to determine the thickness of my domains. So that way I could confirm whether or not my domains were monolayers. Now on to my results. I first optimized the growth temperature. So I examined a range from 750 Celsius to 1050 Celsius. And by using Raman, I was able to find the full width half maximum value. You can see those values here. And basically, these tell me the sharpness of my primary Raman peak, which directly correlates to the crystallinity of my domains. So a lower full width half maximum value means better crystalline quality. And from this data, I was able to determine an optimal temperature of 900 Celsius, as this temperature gave me the largest domains with the best crystalline quality. After temperature, I optimized the time of growth. So I found that growing for under 10 minutes led to domains with very poor crystalline structure. You can see this from the 5-minute image. They're more amorphous than crystalline. However, if I grew for more than 10 minutes, the domains would grow too large, forming this continuous film that you can see here. And this film just had too many layers and too many grain boundaries for electronic applications. So I was able to determine an optimal duration of 10 minutes. The last parameter I optimized was the molybdenum flux. So I found that if the flux was too low, only small domains would grow, if any at all. However, I found that increasing the flux led to these bilayer islands. So to avoid these bilayer islands, I had to find a balance between the growth temperature and the molybdenum oxide mass, which I determined to be 900 Celsius and approximately 10 milligrams of molybdenum oxide. So here's my optimized recipe and some images of the successful growths that I've achieved by using this recipe. This here is an optical image, much like the one I showed earlier, and this is a scanning electron microscopy image. And really, both of these images just illustrate large, uniform MOSE2 monolayers. So in conclusion, I had great success in growing molybdenum diselenide monolayers using chemical vapor deposition, and I was able to develop an optimized recipe. I also determined the effects on growth of various parameters, and these findings could contribute to future research in this area. And in terms of future work, my recipe could be further optimized by tweaking the gas flow rates, the substrate material, and the substrate positioning within the furnace. I will now open up to questions. Thank you very much.
Any questions?
Hello. My name is Brian Barinanko from the University of Maryland, Baltimore County, Mechanical Engineering. And my question to you, since you were working with molybdenum disulfide, diselenide,
Yes.
will be if those same parameter will be just as effective with other metals?
Okay, that's a great question. So the question is if the parameters for my optimized recipe would work for other TMDs. And realistically, no, because the transition metals in the TMDs, so molybdenum, tungsten, they have different melting points. So right off the bat, the temperature would have to be different. And it really, all the other parameters affect the metals in different ways too. So it wouldn't work for other TMDs, but good question.
Hi, so you mentioned that you were trying to optimize the crystallinity of your structures. I was just wondering what effects that crystallinity has on improving the, I guess, electronic properties of your material.
Yeah, also another great question. So you asked what effect the crystallinity has on the electronic properties of the material. And really it just comes down to the more pure and crystalline that the material is, the better electron carrier mobility it has. So it's basically just able to transfer electrons faster, and it has other electronic properties that are improved as the purity and crystallinity goes up. But sometimes you do want to introduce defects, as defects, can change the properties for specific applications. But good question.
Those larger domains that you showed, were those single crystals?
Yes. Well, actually, not all of them. So right here, you can see a lot of the crystals will kind of come together, which is all right. It introduces grain boundaries. I'm sorry, I forgot to repeat the question. The question is if all of these domains are single crystals. So some of them are single crystals morphed together, which introduces grain boundaries, which aren't necessarily ideal for electronic properties, but they are manageable. It'll still work, and you can see that some of these domains are single crystals. So this right here would be a single crystal. This would be a single crystal.
How do you know that?
Yeah, well, we're able to determine from previous work, which is all of the single crystals form in either hexagons or triangles. So, and we're able to tell if it's two crystals, then they'll have formed on top of each other at some point. So, by using the photoluminescence data, we're able to determine it would be a bilayer at that point, is what I mean. And so we can determine whether it's a single crystal by if it's all continuously a monolayer, or if there are some points where there are bilayers due to crystals stacking or forming on each other.
Okay. All right, let's thank our speaker one more time.